All right, we know that the derivative of x cubed is 3x squared. Now, notice we've been using, all the way through chapters 1 through 6, we've been using ddx to denote the derivative. So the way that we're going to denote the antiderivative is with the integral symbol. So anytime, David, you see the integral symbol, what you're doing is you're taking an antiderivative. So the antiderivative of 3x squared is x cubed plus some unknown constant. We know the derivative of the square root of x is 1 over 2 square roots of x. So the antiderivative of 1 over 2 square roots of x is the square root of x plus c. The derivative with respect to t of tangent t is secant squared t. So the antiderivative of secant squared t is tangent t plus c. The derivative with respect to u of u to the 3 halves is 3 halves u to the 1 half. So the antiderivative of 3 halves u to the 1 half is u to the 3 halves plus c. Okay? Now, there's something that you need to know about the antiderivative. Do you see right here where it says dx? That right there is needed because that tells you what the variable of integration is. That tells you what the variable of integration is. Now, for us Calculus 1 students, we only deal with single variable functions. Okay, a function is a function of x, usually. Sometimes it's a function of t. All right? So it doesn't seem to have, it still has great meaning. It's more than what I'm just telling you now. But when you get, if you ever take Calculus 3 in college, you're going to be dealing with multivariable calculus, and then you need to know which derivative, which variable you're integrating with respect to. Okay? So the dx is there for a purpose, and you need to make sure that you also write dx too. So you're not just integrating or taking the antiderivative of 3x squared, it needs to be 3x squared dx. Okay? Same thing down here. The variable here is t, so it needs to be the integral of secant squared t dt. Okay? So while it doesn't play a huge role, it does play an important role. And there's more meaning than just what I've told you. I mean, it means more than just that's the variable of integration, but I think that's a good way to at least first explain it today, okay? All right, so it turns out that there are a lot of things that we can already anti-differentiate because we've been doing derivatives now for about 6 months or so, okay? If we know that the derivative of x is 1, then the antiderivative of plain old dx, which is 1 dx, should be x plus a. If the derivative of x to the r plus 1 over r plus 1 is x to the r, assuming that r is not negative 1, then the antiderivative of x to the r should be x to the r plus 1 over r plus 1 plus c, assuming r is not negative 1. By the way, if it is negative 1, then you've got a very special case there. The derivative of sine is cosine, so it makes sense to say that the antiderivative of cosine is sine plus c. So do you already see that there's a lot of antiderivatives you can already find? And it's probably the trig functions that you've got to be a little bit more careful about. Remember, the derivative of normal cosine is negative sine, right? So if you take the derivative of negative cosine, you get sine. So if you integrate sine, you get negative cosine plus c. Differentiate tangent, you get secant squared. So anti-differentiate secant squared, you get tangent of x plus c. Differentiate negative cotangent, you get cosecant squared. So anti-differentiate cosecant squared, you get negative cotangent x plus c. Differentiate secant, you get secant tangent. So anti-differentiate secant tangent, you get secant plus c. Differentiate negative cosecant, and you get cosecant cotangent. So anti-differentiate cosecant cotangent, and you get negative cosecant x plus c. E is that wonderful function that's the derivative itself. So differentiate e, you get e. Anti-differentiate e, you get e to the x plus c. Differentiate b to the x over ln b, and you get b to the x. So anti-differentiate b to the x, and you get b to the x over ln b plus c. Differentiate natural logarithm of absolute value of x, and you get 1 over x. Anti-differentiate, and you get ln of x, absolute value, by the way, ln of absolute value of x plus c. Okay. So we've seen those before then. We know what those are. Okay. Okay. 7.2.3. A constant factor can be moved through an integral sign. That is, if you have a constant, the antiderivative of a constant times f of x dx, that is the same thing as pulling the constant outside the integral and saying the constant times the integral of f of x dx. You're allowed to do that. Part B, if you have the integral of a sum, then you are allowed to rewrite that as the sum of two integrals. So the integral of f of x plus g of x is equal to the integral of f of x plus the integral of g of x. Same thing with the difference. If you have the integral of f of x minus g of x, then that is the integral of f of x minus the integral of g of x. So in other words, another way to say that, David, is the integral distributes over sums and differences. Over sums and differences. Okay? All right. So here's some good examples right here. So let's actually just do some examples. Let's go ahead and do some. Let's say I wanted to find the antiderivative of pi sine of 2x dx. The antiderivative of pi sine of 2x dx. That's exactly right. Pi is a constant factor, so this becomes pi times the antiderivative of the sine of 2x. Now, I want to find a function that differentiates to give me the sine of 2x. Well, I already know that it's going to be a negative cosine of 2x. But remember, if I differentiate negative cosine of 2x, what happens? Yeah, the chain rule brings the 2 out. So how do I compensate for that? Because I don't have a 2 out here. It's going to be a 1/2. That's exactly right. So this becomes pi times negative 1/2 cosine of 2x. And so, plus c, by the way. Gotta have that. And so you get negative pi over 2 cosine of 2x plus c. And there's the antiderivative. Now we just differentiate it to show that we have indeed got the correct antiderivative. Now, just like the integral rule here, Carrie, I can distribute that d dx just like I can the integral. So this becomes the derivative of negative pi over 2 cosine of 2x plus the derivative with respect to x of a constant. And by the way, we already know that's got to be 0. Just like the integral, this negative pi over 2 can come out. So this becomes negative pi over 2 times the derivative of cosine of 2x plus 0. And now it's time to differentiate cosine of 2x. So this is negative pi over 2 times negative sine of 2x times 2. And the 2 divides with this 2. These are both negative, so they become positive. And we're left with pi sine of x. And now I know that this is the correct antiderivative because I've used differentiation to verify it. That's what I said. Sine of 2x. You just didn't let me finish. No, thank you. I forgot about the 2. There we go. Sine of 2x. There we go. Does that make sense? Mm-hmm. Good. All right. Same song, second verse. Could be better. Gonna get better. Okay. All right. Let's do some cool stuff here. All right. I want to take and find the antiderivative of x times 1 plus x cubed dx. Not take it out, but do what? Yeah, sometimes it's better to distribute. And this is one of those cases. Yes. So what I'm going to do first, McKenna, is I'm going to write it like this. And then I'm going to use the fact that since this is a sum, this is the antiderivative of x plus dx plus the antiderivative of x to the 4th dx.
So it's 1/2 x squared plus 1/5
plus c. That's correct. That's exactly right. So the rule here is that sometimes you will need to distribute. Doesn't always work, but sometimes it works. Okay? All right. Let's find the antiderivative of 2 over x plus 3 e to the x dx. Okay, we have a sum rule, so this becomes the integral of 2 over x dx plus 3 times the integral of e to the x dx. But even this 2 right here, McKenna, I can pull that 2 out to the front. So this is 2, the integral of 1 over x dx plus 3 integral of e. Did I lose you there?
No, I'm saying it works out now because that's ln.
Yes. Now it's not just ln x though. This is where you have to be careful. It's ln of, go back to that table real quick in the book. Absolute value. So this becomes 2 ln absolute value x plus 3 e to the x plus c.
Wait, why is ln value have to be absolute?
Yeah, it has to be absolute value. Why?
Give a negative ln.
Mm-hmm. Why the absolute value? The answer is this. Right here, Carrie, do you see 2 over x? You are allowed to put negative numbers into this expression right here. So if you anti-differentiate, you should also still be allowed to put negative numbers into the antiderivative. If you don't have the absolute value, that becomes a problem.
So it's undefined.
Yeah, if I didn't have the absolute value here, then I wouldn't be able to put any negative numbers into this logarithm because the logarithm of a negative argument is undefined. It's not a real number, right? So because we're allowed to put negative numbers into the original function, we should still be allowed to put negative numbers in its antiderivative. Does that make sense? In other words, when you go up the ladder, whatever numbers you are able to put in the derivative, you definitely should still be able to put into its antiderivative. If you lose numbers like that, if you didn't put an absolute value, you'd be losing potential numbers. And that would be a loss, and you can't have a loss. So the way that you overcome that is you have the natural logarithm of the absolute value. Does that make sense? Okay. All right. Export. Okay. Next up, let's do something really cool. All right. Antiderivative of secant of x times secant of x plus tangent of x dx. Now, let's say that this is Sally, and Sally is a beginning calculus student just like you. And so this is what Sally does. Sally says, hey, since this is secant of x times secant of x plus tangent of x, I can pull out that secant of x and say secant of x times the secant of x plus the tangent of x. Has Sally done a good or a bad thing? Okay, we are saying that she has done a bad thing. Now, why has she done a bad thing?
It's not a constant.
This is not a constant. This is a function of x which you're trying to integrate. So this is a no. Okay, so because this is the imaginary world, we can hit Sally over the head with a baseball bat.
Redistribute.
Yes. So, what'd you say? Yes, it does. But I just wanted to make a note of that now because I haven't in the past, and I noted that when I didn't make a note of it, my students had a tendency to think they could do it. So you can only pull out constants, factors that are constant. So yeah, distributing that secant becomes way nicer. So this is secant squared x plus secant x tangent x. And now we can separate them using the addition rule for integrals. So the integral of secant squared x dx plus the integral of secant of x tangent of x dx. Notice how I'm very careful here, Carrie, to make sure I always put a dx in every integral. I'm not always that careful, and if you see me make a mistake like that, you need to let me know, because I do sometimes skip that. But I need to make sure that I have a dx for every integral. Okay? Well, this has a nice immediate antiderivative. It's tan x. And this has a nice immediate antiderivative. Yeah, secant of x. And then I need to make sure that I say plus c. You guys are awesome. And this is one of the reasons why the integral calculus at this stage feels a whole lot nicer than the differential calculus, because the integral calculus, you've been doing derivatives for so long, you can almost say, look at it and say, oh, well, that's got to be the antiderivative, right? So remember, a long time ago I promised that when you got to this stage of calculus, you would find the beginning parts of this part of calculus a lot, I won't say easier, but a lot more intuitive than what we did in the differential. So you have worked hard, so this is the payoff. All right. Now, tricky, tricky.
Could you bring the x to the numerator?
Can I bring the x to the numerator?
Since it's x to the negative 1.
That is a definite possibility, yes. So I could do this. You mean like that? That's totally doable? Okay, what would you do next, David?
Do log distribute.
Yes. So what do you get when you distribute x to the negative 1? X squared
Plus 2 plus 3x.
That's correct. Now we can split everything up. Now I'm going to bring my constants outside.
And that's the same as 1 over x.
Yeah, I'll put that back down there.
So 1 half x. Oh no, 1/3 x
Yep.
plus c.
Now remember, this is dx.
With 1.
It's 2x.
Yes.
Okay, yeah. Plus 3 ln x plus c.
Plus c. Shabang.
Is there another one here?
Yes, there is. Some people, instead of saying, raising the x up and saying x to the negative 1, which by the way was beautiful, some people just split it up into 3 different integrals like this. They'll say the integral of x cubed over x dx plus the integral of 2x over x dx plus the integral of 3 over x dx.
They pretty much do the same thing. So you get some-
Yeah, this becomes the same thing here, doesn't it?
Yeah.
Oh, it's a different way.
Exactly. It's a different algebraic approach that yields the same answer. That's exactly right. And that only works, though, David, because this right here is a monomial. So whenever you have monomial divisors, this is a good technique. Monomial divisors.
Well, what happens when it's not?
Okay, well, then you have new things, right? What I'm trying to do now is I'm trying to teach you all the ins and outs of, there's no one way to do it. You've got to learn all the different strategies and techniques and all that. Okay? Does that make sense? Okay. Notes 3. All right. All right, let's check out this bad boy. The integral of the sine of x over the cosine squared of x dx.
Cosine squared of x is the same as cosine x squared. Or parentheses. Cosine x squared, right?
Cosine x squared?
Sine of
Okay, let me go back to your question. You asked, is cosine squared x the same thing as cosine x squared?
Parentheses around the x and that.
Like that? That's correct, yes. That is correct.
And then sine over cosine is tangent.
Okay,
So that's cosine
And 1
squared.
over cosine will be
so this becomes sine of x over, can I write it like this?
Times
Yes. Ha ha ha. You guys are good.
Which is
That's
tangent
tangent.
upon secant.
Yep. You got it. You cracked the code. Very good.
Oh, tangent x, secant x,
Secant of x
plus
plus c. Which reminds me of what happened one time at Dysarts. Two math professors from UMaine went to Dysarts to talk about, the various things that they were working on in mathematics. And the waitress came up and she took their orders for drinks. When the waitress walked away, one of the math professors was lamenting about how mathematical education was getting more and more difficult and people were growing up without understanding a lick of understanding in mathematics. So he went up and he went to the bathroom. Well, the waitress comes back to the table and the other math professor says, "Hey, I'll tell you what. When my partner comes back, I'm going to ask you a math question. And I simply want you to say e to the x. I just want you to say e to the x. And if you do that, here's $20. Would you do that for me? Would you just say e to the x?"
He's paying her $20.
He's paying her $20 to do this. She says, "Sure, honey, I'll do that," as the way waitresses do. So she takes the $20, she walks away. Well, his friend comes back from the bathroom and they're talking again, and the waitress comes with their meals. And so the professor says to her, "Excuse me, can I ask you a question?" "Well, sure, honey, you can do that. What's the integral of e to the x?" And she says, "E to the x." And the other math professor was amazed. And so she walks off, and the math professor thought, well, maybe people do know mathematics. But as she was walking away, under her breath, she said, "Plus C, you moron." Yes,
For your, I'm just working on an exam schedule, so
Yes.
sorry to interrupt.
that's okay.
Your advanced computer class, do the kids use their own laptops or do they go down to the lab?
They have their own lab.
So they could do their exam in your room? Okay, all right, thank you.
That's fine.
So, but now I've been waiting to tell that joke all year. So now you have that joke. It may not be very edifying to say plus C, you moron, but that's the way the joke goes. So, okay. Nothing like good lame math humor. Okay, what if we have the integral of 1 over theta minus 2e to the theta minus cosecant squared theta d theta.
Can we split it off?
Correct. This becomes the integral of 1 over theta d theta minus 2 times the integral of e to the theta d theta minus the integral of cosecant squared theta d theta.
so this is ln absolute value theta
Correct?
minus 2 e to the theta
Correct.
minus that's cotangent.
Yeah, now is it a minus or a plus?
It's
Isn't that cosecant of theta?
No. This integrates to either, what does this cosecant squared integrate to?
okay. It's going to be negative cotangent, but it's positive
Because of the negative that already exists out here. Yes. So it becomes plus cotangent of theta, and then plus c. Good. Okay. And that is all.
Is it going to be what we did right there?
What'd you say?
Is all of that, is all the homework going to be like this?
Yeah. And so what I'm going to do next, God bless you wherever you are today.